In this video, we're going to learn about metallic bonding. So metals are atoms with very few valence electrons, and they have a lot of empty atomic orbitals as a result of that. So let's consider, for example, scandium, which is D1. So scandium is going to have 4s electrons. It's going to have 2 of them. And then it's going to have, in the 3D, it's going to have 1 electron, and then 1, 2, 3, 4, 5 d orbitals. Notice there's a lot of space here for electrons. I'm going to just skip the rest. But there's a lot of space here in the valence shell for electrons where there can be bonding. And what's kind of interesting is that the 3D from one scandium atom and the 3D for another scandium atom will actually interact with each other. Even though there are no electrons in them, they will create more possibilities for electrons to come into. And so that will allow the electrons to flow throughout the whole metal, the whole macroscopic metal. So if I've got a chunk of scandium, really the valence electrons, these 3 valence electrons, the 4s and the 3d, they aren't really assigned to any specific atom. They're going to be delocalized among the whole chunk of scandium metal that I have. So what we can do is we can view metals as being a sea of valence electrons among a bunch of fixed ions. So here, we're going to look at this as though it's a group 1 metal. If this is a bunch of lithium, then we've got a lithium cation with a positive 1 charge, and its electron, which is not associated with this particular lithium atom. This electron is here at the moment, but it's going to be over there the next moment. And the electron that's over here will be over there in the next moment. That's just the way it works with metallic bonding. Electrons are delocalized and they're allowed to freely move throughout a substance. So the delocalization of electrons give metals their unique properties. For example, they're very shiny, they're very lustrous. And this has to do with the fact that they can absorb or emit nearly any light, and that's because of these orbitals that are empty interacting. I've drawn an atomic orbital diagram for scandium here, but if you had the whole scandium structure, because all the orbitals are interacting with each other, you would find many, many, many more possibilities, and it basically changes you from having certain discrete values of 4s and 3d and et cetera, 4p, right? Instead of having these gaps between them, you're going to have some kind of weird hybrid that has 1 energy, and then a different weird hybrid that has just a little bit more energy than that, and another weird hybrid that has a little bit more energy than that. So you end up having a kind of continuous spectrum of absorbance that basically any light can be absorbed by any metal. And also, once the light is absorbed, it will also be emitted, again, at pretty much any level, because there are so many different possibilities for electrons to hold energy. Additionally, metals are very malleable and ductile. They're very malleable, meaning that they can be hammered into shape. If you try to do that with, say, an ionic crystal, you wouldn't have that be a possibility, because in an ionic crystal, we have Na plus and Cl minus, and I'm going to put a Cl minus here and an Na plus here. And let's just say I took a hammer and I hammered this and I pushed down here. Well, I would have sodium and chloride here, but because these guys got pushed down, my chloride would be here and my sodium would be here. And actually, I'm going to draw another sodium here just to really show Na plus and Cl minus. I'm now making there be a little bit more. and Cl minus. There we go. So notice I get repulsion here between the chlorides and repulsion here between the sodiums. That happens in an ionic compound. That is why if you hammer a crystal, it's just going to break apart. It's going to fracture because of that repulsion. In the case of metals, if I just have some sodium metal, the sodium metal is never going to repel more sodium metal. Even if I hammer these, I just get Na and Na and Na and Na. These two are not going to repel each other. So that's why metals can be quite malleable. And ductile as well. Ductility has to do with the ability to turn something into a wire. Metals are very easy to hammer into sheets or whatever shape. They're very easy to turn into a wire. Metals have these properties of malleability and ductility. I finally want to mention the strength of of metallic bonding, which does vary. It depends on the substance that we're working with. The strength of the metallic bond correlates with nuclear charge and atomic radius. So if we look here in group 2, beryllium is going to be with more of a nuclear charge than lithium. Beryllium is with 4 protons rather than lithium's 3, and beryllium therefore has a stronger metallic bond. And you can kind of look at this through the lens of Coulombic attraction. With Coulombic attraction, we have, remember, we're almost talking about a beryllium ion, Be plus 2, and 2 electrons. Well, in the case of lithium, we have a lithium positive plus 1 valence electron that is delocalized, right? And so with a higher charge here in beryllium, we get more Coulombic attraction than we have with lithium. You can see as we go across, that trend holds in every case. But as we go down a group, we're getting to larger atomic radii. And again, think Coulomb's law, as the nucleus is further separated from the valence electron that is really delocalized, you have less of a nuclear pull, so you're going to have less attraction. And that is how we can explain trends with the bond strength in metals. So I hope this video has been helpful to you. Please let me know if you have any questions or comments in the comment section below. Thank you very much.